is really kind of one of the core concepts for the course. And we're going to be covering a lot of material, and it'll be your first real experience using some of these tools like hypothesis testing. One thing I want to mention is that we'll be covering this a lot, and today I'm going to give you a lot of material on this. And just so you know, you're going to be seeing a lot of this material in other ways in the future lectures. So it'll start to come together, even if it doesn't, if you don't understand everything exactly today. Okay, so this is actually one slide from last class. This is basically just a review of actually the binomial distribution. So if you have an event A and occurs with this probability PA, that if you're going to repeatedly do n trials, which means that you have this basically you have n trials. Each trial, the probability of event A is PA. The question is, how many times will event A occur out of those n trials? Okay, and it'll be approximately normally distributed with mean NPA and variance NPA times 1 minus PA. Okay, this only happens when you have a lot of trials. Okay, why? Because when you're only having one trial, there's two possible outcomes. That's like a discrete event, right? But when you have a lot of trials, it's kind of, you can think of this as the number that you get. That's kind of like a continuous outcome. So the normal distribution is a continuous distribution, right? So, okay, so that's how we write it. We write NA is normally distributed. This is the mean, and this is the variance. Okay, so then how do I convert, let's say, like the number? So if I say, let's say that you have n trials, let's say 20 trials, and something occurs 12 times out of those 20 trials. How do I convert that number 12 into a frequency? This is an easy question. I'll give you a hint. Do you divide by 20, right? So dividing by 20 is multiplying by 1 over 20, right? Or the general formula is you just take this random variable NA, right? Multiply it by 1 over n, okay? And remember the rules for multiplying by a scalar. The mean gets multiplied by that scalar, so you get NPA times 1 over n, which is PA. And the variance, what happens to the variance when you multiply by a scalar? You multiply by the scalar squared, right? So 1 over n squared, one of those n's cancels this top end, and you have a n at the bottom. Okay, so that's the frequency. So this is just the distribution of the frequency, and we always put a hat on there. The hat always means the observed quantity, right? While the unobserved is the PA, right? When we write a hat, typically what we say is it's the estimate of that parameter from the data. Okay, and the frequency, just taking the number of trials divided by n, that turns out to be an estimate from the data, because if you look at this estimate, the mean is PA. So that means it's a good estimate. Okay? But we always put these hats. So hats always mean observe, something that you see, and the without the hat, that's kind of the theoretical quantity that we never can really observe it. Okay, so now let's apply this to association studies. So for association studies, we're given, let's say we're given n over 2 case and n over 2 control individuals. So what does that mean? So cases are individuals that have a disease. Let's say n is 1,000. Okay, so let's say I have 500 individuals that have diabetes and 500 individuals that don't have diabetes, out of a total of 1,000 n. Okay, and so since each individual has 2 chromosomes, the total number of chromosomes that I'll see will be 1,000 case chromosomes and 1,000 control chromosomes. Okay, and so let P plus A and P minus A be the true frequencies for the cases and the controls. Okay, so you can imagine that, let's say hypothetically, for example, 60% of the case chromosomes will have a variant, and 40% of the control chromosomes will have the variant. Okay, that's like theoretically. Like if basically what we're saying is that a diabetic individual will have 60% chance will have the A there, and a non-diabetic will have a 40% chance. So we don't know those. If we knew what those numbers were, we wouldn't have to collect any data. We could just, we would know what we're looking for. But here we collect data, and so at SNP A, we collect, we measure, and actually if there's some kind of a typo, this is PA plus a hat. The hats got really separated here, but that's the hat. So these are the observed case and control frequencies. So what did I do? How did I compute these frequencies? I basically take, let's say, let's say in 612 of the case chromosomes, I saw the SNP, the variant. So I divide by 1,000, and so then that would be my frequency. So these are the two frequencies. And so we know that these two frequencies, basic observed frequencies, follow this distribution. Okay. So now what I wonder is that how can I tell if I give you these two numbers? Okay. How can I tell if this variant is involved in diabetes? Intuitively. So for example, what if this one is 0.63 and this one is 0.28? Would you say it is? Yeah, so what did you do in your head? You kind of subtract them to see if they're different, right? Okay. What if this was 0.62 and this is 0.63? So maybe not, right? Okay, but you basically subtract. So so we're going to use the fact that they follow this distribution to figure out a statistical test. So if you remember from last class, what our quantity of interest basically is going to be kind of the difference between these two guys, right? Because that's going to be a measure of how, like how much does this variant maybe affect the trait, right? So it's going to be our starting point. Okay, so basically if these are the two quantities, if these are the observed frequencies, what if I take the difference? Okay, what is this difference? So this difference, what's the mean of this difference going to be? What rule do we use? So it's going to be the mean is going to be the difference in these two means, right? And then what's the variance going to be? It can be the sum of these two variances, right? Okay. You notice I did this little factoring here thing where I pulled out the n, right? Okay. So now, so here now I'm going to say, so if I want to turn this into a standard normal statistic, what do I want to do? I'm going to want to divide by the square root of the variance. Okay. But before that, I can just kind of approximate this number with this, okay, where I'm saying is that, I'm saying that the overall frequency is going to be the average of the case and the control frequencies. And I'm going to say that this is going to be approximately equal to that, okay? And then, so then if these are equal, then this statistic which is going to be this, is going to be normally distributed with mean 0 and variance 1, okay? So why is the mean 0? Well, yeah, because if these guys, this is going to be, it's going to be this distribution, this statistic, divided by something, like, some variance, right? So if the mean is, if these two are the same, which is what I'm assuming, okay, because that's the null distribution, I assume that there's no association. These two are the same, then what happens? This is going to be 0, right? 0 divided by any number is still 0. Okay, so the mean is 0, okay? And what number do I divide it by? I divide it by basically the square root of this guy here. Okay, if I divide by the square root of this guy here, what will happen? It's kind of like multiplying by 1 over the, of this number, which will turn it into a 1. Okay, so that's this statistic here with just some factoring and making this assumption is exactly the same as this guy here. Okay, so that's why you get mean 0 and variance 1 if there's no association. Okay, so now if I give you these two numbers, you plug it into this value, you get some kind of a score, how can I determine if it's significant or not? It's from this is kind of a review from last class. And we're going to do lots of examples, so don't panic too much. Yeah, we can see if it's basically where it falls in the distribution, right? Because see, this is now, look at the nice thing about this. This number, which is, we basically plug in the observed data into this, and we get this number. And we know which distribution it follows. So we know something about this distribution. So what we could do is, we know that the data is going to follow this distribution. Okay? And if that's the case, we can see if it's really significant, if it's in the tails of the distribution. Okay? If it's in the tails of the distribution, what that basically is saying is that it's significant. Okay? Why? Because this is the distribution if we assume that the SNP has no effect on the trait. Okay? So then what we do is we compute kind of how likely is that. Actually, what we're really computing is we're computing how likely is that or something more extreme. Okay? And if that's an extremely small number, then what that suggests is that our assumption was wrong, that the SNP has nothing to do with the trait. Okay? So do you guys learn proof by contradiction, maybe in math or in algorithms? Okay, you guys took algorithms, right? Some of you. So this is the same kind of idea. Hypothesis testing is that thing. You assume there's no effect. So we assume that there's no effect. It should come from this distribution. And we basically see how likely is that. Okay? How likely is that or something more extreme? So that way if we're in the tails. And so then this is the basic formula. So we plug in our observed values here. This is, we have our threshold. If we're basically less than this value or greater than this value, then we say that the association is significant. Okay, so let's do an example. Okay, so this will help put things together. So let's say our significant threshold is 0.05. Let's say we have 100 cases, 100 controls. So the genotype has these alleles, right, 0, 1. We assume that, so because we have 100 cases, 100 controls, we're going to have 200 case chromosomes and 200 control chromosomes, because each individual has two alleles. We're going to observe, let's say it's 120 ones in the cases and 110 ones in the controls. So the question is that significant or not? Okay, what we do is, here's the frequency in the cases, here's the frequency in the controls, here's the average frequency. This is going to be the frequency for that denominator. Okay, so we compute those three guys. Then we just plug it in, these are them again, into this formula. Okay, and we're going to get this value, 1.01. Okay, so where's 1.01? 1.01 is here. So is that significant? No. And looking back, does that sound like it's 110, 120? Does that sound like it's significant? No, right? Yeah, so it makes sense. So far it kind of works. Okay, this is actually here what I'm showing is that when you say significant or not significant, that's kind of a binary thing. Either you are significant or you're not significant, right? There's another measure which is called a p-value, and we'll talk a little bit more formally about it in a second. But you can think of intuitively, it kind of quantifies how significant something is. Okay, and what the p-value is, the way you think of it is, the p-value, if you have a certain observation, the p-value tells you what's the threshold need to be for that observation to be significant. Okay, so based on that, what if I see exactly a value of 1.95? If I'm exactly here on that point, what would my p-value be? We're kind of going ahead a little bit. It's going to be, well, it's going to be actually 2.5%, but really it's going to be 5.05, right? Because this is, because this threshold, this 2.5% comes from 5%, half of it, right? So the p-value is here. So the question is, what if this purple region was extended all the way to here, and then this guy, SA, would be exactly on the boundary. So the question is then, how big is that purple region? Okay, so you can see how how and this is how you compute it. It's actually going to be about 0.31. Okay, so intuitively you see how like if you landed right here, you'd be exactly at 5%. You can imagine if you landed right here, you'd be even something smaller. So you can imagine the p-value is kind of a way to measure the level of significance. Okay, we'll talk more about this, but I just want to put this up here. Okay, here's another example. Let's say you see 130 versus 110. Okay, that's obviously more significant? Do you think it's significant or not? Huh? No? Okay, no? Yes? You guys can look ahead in the slides and like get all these right if you wanted to, okay? Okay, so here's the numbers, okay? 2.04, okay? 2.04, yes, it actually is significant. It's right here. So if this was exactly at the threshold point, the significance would be 0.042, right? 0.042 is really close to 0.05, right? So for those of you that guessed incorrectly, okay, understandable, right? It was pretty close. Actually, let's look at, so in order to compute the p-value, we want to compute the area of this curve moving forward, okay? So how could I do that? Using the PDF and CDF and all that kind of stuff. I mean, I tell you kind of right here, but in general, there's lots of different ways to do it, right? So I observed 2.04. So how do I get the p-value? I want to compute the area of this curve, right? What's the easiest way to do that? The area of this area from 2.04 onward. How do I do that? Yeah? Huh? Yeah, the CDF. So if I type in the CDF of 2.04, I'm going to get actually 0.979. But that's not my p-value. So if I do 1 minus that, I'll get 0.021. It's still not my p-value. Huh? Then double it, right? And then guess, yeah, it's easy when the answer's here and you can just keep trying stuff until you get it right. Yeah, but the reason is because the threshold is going to be this area plus this area. So there's a lot of ways to compute this, okay? For example, if you have a positive number, it's kind of a pain because you're going to get some really big number, right? What if I took the negative of this guy and I typed in the CDF, what would I get? I would get this number right away, right? Okay, so one formula for this would be, of the p-value would be negative absolute value of, the negative of the CDF, the CDF of the negative absolute value of what you observed times 2. Okay, that's one thing. Another thing you can do is, if it's greater than 0, you compute the PDF, you take 1 minus this, and you multiply by 2. So there's many different ways, right? Or you can do a combination. You can take 1 minus this one plus the negative whatever thing. So there's lots of different ways you could do it, okay? That's the p-value. Okay, here's another example. Now I increase the number of individuals to 1,000 cases, 1,000 controls. So you have 2,000 chromosomes. And what do you see? You see 1,200 ones and 1,100 in the cases and 1,100 ones in the controls. Okay, so this is actually, if we remember, this is the same frequencies. These frequencies are the same as in our first example that wasn't significant. Okay, but do you think this is significant now? Okay, yeah, right. Obviously, I wouldn't have put it in the lecture notes if it wasn't, right? So, okay, so it's significant. Why? Because you have more individuals. So these guys are the same, but when you divide, you're dividing by this number, which is a small number, so you're going to get a much bigger number, and so it's 3.19. So it's actually over here, and the p-value is 0.0014, so it's much more significant. Okay, okay, so that's okay. So I don't know why this is here. This is okay. Okay, there's a We just went through these. There's some problem with the slides. Okay. Okay, so now we just went through these. Okay, so now I'm going to introduce another so is there any questions on this association studies so far? Okay, so we'll do lots of examples. For those of you that haven't taken statistics, many of you took probability. Many fewer of you took statistics where you do hypothesis testing. We'll do lots of examples. It'll start to make sense. Okay. So now, but any questions on that, or you guys are okay? Yeah.
Can you define null hypothesis again?
Okay. Yeah. Null hypothesis is it's a great question. The null hypothesis is the assumption that there is no effect. Okay. So if you remember last class, we talked about whether computer scientists stay up at a higher rate than the population, and the population, let's say, stays at 25% of the people in the population stay up late. So the null hypothesis would be to assume that the people in the class stay up late at 25% of them stay up late. Okay, so with association studies, the null hypothesis is that the variant does not have an effect on the disease. So the null hypothesis is saying that the frequency in the cases and the controls is the same. That's what the hypothesis is, right? Which basically means that the difference between the two frequencies is 0. Okay, so the null hypothesis is always you assume that there is no effect. Okay, that's a good question. Any more questions? Okay, okay, good. Okay, so now power. Okay, so now power is kind of one step beyond that. So we talked about association, like if you get a study, how what is how do you evaluate it? Okay, how do you analyze it? And then then based on what the data says, either it's significant or not significant. Okay, so power actually has to do with the following concepts. Okay, it's basically saying let's now assume that there is an association at the SNP. Okay, so the SNP is actually involved in the disease, okay, which means that these two guys are different, okay? So let's say, you actually assume that you know what these two values are. And so now the question that you want to ask is, if you collected n individuals in your study, and then you basically measure their frequencies, plug them into the statistic, and then assume the null hypothesis, and then computed whether they're significant or not. So if you did what we did in the previous slides, those examples, the question is, what's the power measures, what's the probability that this would be, that your association, you would say that it's significant, okay? So you can think of intuitively, the power is the probability of detecting association if the SNP is actually involved in the disease. Okay, so the reason why with a certain number of individuals, so power is really useful, where you have to decide, how many individuals you need to collect. So intuitively, imagine that you're doing a diabetes study, right? What would you conjecture the power would be if we only collected 50 individuals, 25 cases, 25 controls? So the power would be really low, right? Why? Because, even if you see if there's a strongly associated SNP, in the data, okay, you're not going to, your statistic isn't going to basically be large enough to get to significance, okay? So we're going to, so let's do an example. I think it'll make it a lot clearer. Okay, actually, but before we do that, actually, let's work this out. So let's say that these two guys are not equal. Okay. So then what happens? So what is this statistic here? This statistic, what is its? First of all, what is its variance going to be? Variance is still 1, right? Because nothing really changed. Okay. But what does its mean? Its mean is, this mean is not going to be 0. So the mean is going to be whatever this true frequency difference is divided by whatever you divided it by. Okay? And so then if I take this is just factoring it out. Okay, so what I'm saying is that I raise this square root of 2 divided by n up to here. Okay, and then here what I'm saying is that I'm just taking this whole thing and I'm calling all of these guys lambda a. Okay, this is all lambda a squared of n. Okay, so why do I separate this out? This part actually depends on the disease. So the disease has a certain effect on the trait, like the variant has effect on the disease. Okay, and you kind of don't really control this. This is just whatever biologically it is. But the n, actually, you can control how many people you collect. Okay, so you can think of this is kind of a function of the biology, you know, for whatever it is. You just don't really have that. While this part you can't control. That's why we kind of separate these two out. Okay, so that's the so this is going to be the distribution of the statistic if these guys are not the same. And what is the power? Okay, so this is actually kind of a key slide here, which is that under the so this is going to be the statistic if these two are not equal. Okay, it's going to follow this distribution. Okay, so that means that if these two are not equal, and I'm basically doing a study, and let's say I do a study the same study with n individuals 1,000,000 times, and I just look at the distribution of my statistic, that statistic is going to follow this red distribution. Okay? And so we'll do an example of this in a second. So then when is this one of these observations significant? How do we determine if something's significant? So this is a tricky concept. Okay, we all forgot about significance. So how do we, when is something significant? You take your essay, yeah?
When it's in the critical region.
Yeah, of the null distribution, right? So this blue guy here is the null distribution, right? And let's say this is the threshold here, right? So whenever you end up with your SA in this region, okay, or actually in this region down here, same one, right? Then it's significant, okay? You say it's significant. So now what I'm saying is that if, let's say, your statistic, if we're making the assumption that there's an effect, is coming from this red distribution, what's the probability of being significant?
All of the areas to the right.
Exactly. It's going to be the area of the red curve, okay, to the right of this black line, okay? So let's go over that kind of slowly, right? So again, you apply your technique, you get your data, okay? You put in the statistic, and then you basically get a value. If it's greater than this value here or down here, you say it's significant, okay? So if this is the distribution of those statistics, right, then if I do this 1,000,000 times, right, and that's how let's say I repeat the study 1,000,000 times, okay? I mean, that doesn't make any sense why I would do that, but let's say I repeat the and then what I do is I draw a histogram of the studies, and this is what I get. So the number of significant studies would be all of those studies that are greater than this value, okay? And that's basically the same as the area of the curve beyond this line. So that's the power, okay? So we're gonna do some examples, but that is a concept, and this is actually, I would say, that the trickiest concept that we're going to be covering in the next couple weeks. Yeah.
This is a little nitpicky, but don't we have to do the opposite?
Yeah, we will include it down here, except for you'll see that. See how you can kind of see this line right here? It's hard to see. Okay, that's the line of the red curve. Okay, you can imagine that by the time it gets down to here, it's like so small. Okay, so we do in the formulas, but practice it doesn't matter. Okay, so any more questions on this? This is like really key. Who's confused? Okay, yeah. So question? Just so confused you don't even know how to ask a question? Okay. Okay, that's fine. So again, let's go over this one more time because this is a really key thing. And okay, so blue curve, null distribution. Okay. If there's no association, we'll be coming from this blue curve, right? What's our definition of saying something's significant? Whenever we're above this threshold, right? So if I look at, let's say the threshold is 0.05, what would be the area of the blue curve beyond this part right here? 2.5%, right? That was like previous examples, right? So the question is now I'm saying is that, hey, there is an association. So your data is not actually coming from the blue curve, it's coming from the red curve, okay? Because these two guys are not equal, so you're actually coming from this distribution. So now what I'm saying is that if I tell you that, what's the probability of you being significant? It's going to be the area of this red curve beyond here. It's going to be this area. For example, what if n is like 1 or 0? What if n is 0 or very small? What if n is very small? Then this curve will be like very close to here, okay? And so this area behind the red curve will be small. What if n is like 1 million or 10 million, right? What will happen is that this guy will be way out here, and the area behind this curve will be a lot bigger, okay? Does that help or no? You're just saying that? Okay. You are just saying that? Yeah, question. Yeah.
Why is there no area in the curve next to the other area?
Oh, yeah. Okay, so it's just, in the formulas, there will be. So it's actually the area of this, the red curve down here, plus the area of the same red curve on this side. Okay? Well, it's not repeated. It's just that if this is the actual statistic, okay, let me say this. Let's say P plus is greater than P minus, okay? Let's say this is like the true values are 0.6 and 0.4. You're almost always going to get a positive difference, right? But when you're looking at both sides, you're testing the positive difference versus the negative difference, right? It's so unlikely you're going to be even significant down there. Does that make sense? So you'll see in the formulas on the next slide, we'll cover both cases. Yeah. Yeah. So this actually explains. Yeah, exactly. You're saying that the larger your n. So you can think about it this way. The power actually measures how likely you are to detect the association. Okay. But you can think of really that's purely defined by this single parameter. We call this the non-centrality parameter. Okay. If the non-centrality parameter is really big, okay, what happens? These two guys are really far apart. Maybe this red curve is all the way over here. Okay. So almost all of its area will be beyond this threshold. So the power will be actually close to 1. If this parameter is actually 0, then the red curve and the null distribution are actually the same. Okay? So actually, quick question. If this is 0, what will be the area in this regions? 0.05. Yeah, that's kind of a, yeah, it's actually exactly alpha, right? So that's a good one to try to understand. If you understand that, then you're getting it. Okay. So you can see that the power purely depends on this, and so there's two ways that the power can be affected. One is if lambda a is high, and that means that if the SNP or the variant has a strong effect on the trait, then it's high. The other one is if you have a lot of individuals. So either those two, the product of the effect and the square root of the number of individuals, which defines the power. Okay, it's kind of cool because your ability to your power really only depends on one parameter. So there's a lot of things going on. You have like the P plus, the P minus, whatever, the number of individuals, the disease, whatever. Essentially, everything comes down into that formula to just one number, which tells you how you're going to find it or not. Okay. I want to take actually more questions here because understanding this concept, we're going to go through the examples, but understanding this concept is really critical. If you get this is the hardest concept. So any more that we got this? Yeah. Yes.
So therefore, when you talk about the non-centrality parameter being
Okay, so that's a good question. These are actually not the differences exactly. They are the differences, but then normalized when you divide by the square root of what all that stuff. So the beauty of it is that because you're dividing by that, even let's say the difference, you're kind of taking into account that like a difference between 0.2 and 0.1 is only 0.1, but a difference between 0.4 and 0.5 is also 0.1, okay? But they behave differently because their variance is different. But the thing is that your statistic actually divides by the variance, by the square root of whatever, and so then they behave in the same way. So the nice thing about the statistics is that you kind of throw away all those details. Okay, you basically take everything, when you plug it into here, you actually know the distribution, right? It just depends on, in this case, it just depends on whatever this this parameter is. Okay, it's a good question. Any more? This is good. Yeah.
What quantities do you compare to come up with the non-centrality parameter?
Okay, so the non-centrality parameter is actually exactly this value. Okay, so it's going to be whatever your true frequencies are. Okay, actually, this raises an interesting concept. Okay, power is based on assumptions about the disease effect. Okay, so that it's kind of weird. You're like saying that it's power. The way to think of power is like this. Let me assume that let me assume that there is a effect of the disease that changes that affects the frequency by, let's say, 0.1, for example. Okay, let's assume that. And now, if I had 1,000 individuals, what would my probability of finding that be? Okay, the reason where you use power is you basically power gives you an idea of what you can possibly find in your study. Okay, and so for example, if I have 1,000 individuals, I can compute what kind of differences would I be able to find, and which kind of differences do I not find. Okay, so maybe I can find differences of 0.1, but maybe I can't find differences of 0.05, frequency differences. If I want to find frequency difference of 0.05, I might need 2,000 individuals, right? So power lets you kind of determine, kind of figure out ahead of time what you're going to discover based on the amount of money you're spending. Okay, so that's the idea, right? So these guys are based on assumptions about the two true frequencies, and usually use them as, we'll usually use power to determine whether you'll find something if you do the study. So that's the concept. Okay, that's a good question. Any more? Last one? Yeah.
So whenever you want to rely on power, you have to have some assumption about what the true.
Yeah, power actually is defined based on something. So that's whenever you say the power, typically you say the power of a study is 90%, under the following assumptions. And there's a lot of them. The effect size is this, right? Basically lambda, either you have a lambda or you say the two frequencies are this, and also there's the number of individuals, right? The great thing is when you're doing the null hypothesis, okay, you don't make any assumptions, right? Because you are making an assumption. You're assuming that there's no effect, okay? So when there's no effect, it's simple. This is just zero, okay? There's only one way to assume no effect, which is making this zero, right? There's no, for power, you have to actually explicitly say what all the assumptions are to get that, okay? So yeah, these are complicated concepts. So these are like, we just covered stats 100B in 30 minutes. Okay, this is like all of stats 100B covers a lot of this. Okay, yeah. It's going to be close. It's going to be 0.05 because when we get under this scenario it'd be 0.025, but you'll see in the formulas we actually consider both sides. Okay, so here's an example. Okay, so this is an example. So let's say we have frequency 0.05. These are the two SNP, the alleles. Let's say the true case control are 0.06, are 0.6 and 0.5. the question is, how many individuals do we need to observe a significant association? Okay, so these are if we collect, let's say we collect 100 cases, 100 control individuals. These are the frequencies, right? So then lambda square root of n is going to be this. It's going to be equal 2.01, right? And so SA, our statistic is going to follow this distribution. Okay? I just plugged all this in. This is what my lambda is. So this means that my statistic is going to basically follow this distribution. So this is my threshold, 0.95. And this is actually the formula that you use to compute power. But all it is just computing the area of this red curve over here. And it looks kind of confusing. And there's actually a lot of different ways that you can come up with this statistic. So just whenever, I always think of it in terms of the graphs because it's easier. Okay, but this is just I think the most compact formula. Okay, so this is basically this term, which is going to be, this is the threshold plus the non-centrality parameter, you know, this CDF, right, of that, plus 1 minus the negative threshold plus that non-centrality parameter. Okay, so what does that look like? So this is going to be, if I plug this in, these guys are 0.95, 1.95, so this is going to be negative 1.95 plus 2.01, and then 1 minus this guy. Okay, so what is this guy here? This guy here is phi of 0.06. What is that about intuitively? What is phi of 0? 50%, right? Because that's half of the distribution. So that's going to be about 0.52. And what is this guy here? That's going to be something really big, right? So that's going to, and 1 minus that is going to be 0.52. So actually, this guy here is actually the part of the red curve that's below down here, okay? So it's very close to 0, okay? Because, you know, imagine, I mean, you're basically saying that there is an association having the cases be more frequent than the controls. This part right here is saying, what's the chance of being significant that not only are the controls higher than the cases, but they're also so much higher that they're statistically significant. Okay, so that's basically almost 0, okay? But that's where the formula is. This only kicks in when you have very low power, okay, and that's when both sides are kind of close to each other. But as soon as you have anything like reasonable, this is very close to 0, okay? And so this one, why is this 52? Well, think about it. Look, 2.01 and 195 are very close to each other, right? So the non-centrality parameter is actually very close to the threshold. So about half of it is above the threshold. This isn't completely drawn to scale, okay? I admit. So, okay. So if the power is, so we compute this. Okay. So what's that saying? So if we go back to here, that's saying that if we collected 100 cases, 100 controls, the chance of then doing the study, measuring significance, are we significant? That would be about half, 52%. Okay. So now, what if we, on the other hand, collected 200 cases, 2 control individuals? So this is what we would get. What do you think? The power is going to be higher or lower? Higher. Okay, good, easy one. Higher, right? So so the non-centrality is going to be something bigger. Same thing. We apply this formula. Non-centrality parameter is now going to be 80, you know, after I apply this, it's going to be 81%, right? Why? Because I moved this distribution out farther, okay? Again, this is not drawn in scale, but, okay. So this guy, the mean moved out farther from this threshold. Okay, so now what about 400 cases, 400 controls? Now the non-centrality is going to be like this, right? And the power is now going to be 98%, okay? So for example, what if I, so let's say this is 98%, okay? Does it make sense for me to, this is actually 400 cases, 400 controls. If that's what I'm looking for, does it make sense for me to look at 500 individuals or 1,000 individuals? Or not? Why not? Or why yes? Huh? Yeah, I'm wasting money because I already have so the whole point of power is that I can say if this is what I'm looking for, I have a 98% chance of finding it, right? probably if I go to like 1,000 people, I'll have a 99% chance of finding it, right? It's not worth it, okay? Similarly, if I did the power calculation and I had basically an alpha, like a 6% chance of finding it, okay? Then it's also might not be worth it for me to do the study, with that many individuals. I should increase. So that's the idea behind power is kind of like a planning stage, okay? Yeah. Well, I would say that the higher the better, right? And actually what people typically do is, in practice, people spend as much money as they possibly have, okay? And so they collect as big of a study as they can, okay? And but the reason why people compute power is that the power gives them an idea of what they'll find. So for rare variants, so like actually we're going to talk about this in a second, okay? But you'll see that the rarer that a variant is, the lambda A gets smaller, okay? So people use power mostly to take a data set and say, okay, I'm going to be able to find with reasonable power all the variants that have this effect size and are at least this common. And for smaller effect sizes and rare variants, they won't be able to do that. So that's usually what people do, right? Yeah. And so also the other thing is that if you measure your power and it's like really small, but then you find a lot of things, then you know that something went horribly wrong as well, okay? Okay, that's a good question. Any more of these before we go on? Okay, so now, so these examples assume that we know 0.6 and 0.5, but that seems kind of arbitrary, right? Like we're talking about a disease, how do we know that the cases and the controls are going to be these frequencies? So that's what this next thing is. So this is actually how you do that. So a causal, so if we say like, okay, let's say I have a variant that affects my risk for diabetes, how do I quantify, what does that mean? And also, how does that affect an association study? So the way that people think of these variants affecting disease is something that's called a relative risk, okay? So relative risk is basically the following quantity. Let's say, you have a variant that doubles your chance of having the disease. So that means that, let's say your probability of having diabetes is 5% if you don't have the variant, but then 10% if you do have the variant. So then that variant would have a relative risk of 2. Does that make sense? Okay. So what we're typically interested in is finding variants with a certain relative risk, and that so let's look at the question is let's say a variant has a frequency of 0.4 in the population and has a relative risk of, let's say, 2. How does that translate to a case and control frequency? That's a question. Okay? And this is actually a lot of equations, and I put this here because you can use them as your notes, but we'll go through them and you'll have opportunity to also, since the slides are available. But let's look at this, okay? So this is definitions. PA is what? The allele frequency of the SNP. F is the disease prevalence. That's basically how often it occurs in the population. And plus or minus, let's say, is the disease state. Okay, so now if I what I'm interested in is what? I'm interested in the cases, what's the frequency going to be, and in the controls, what's the frequency going to be. So that's what are going to be these guys. I'm interested in P plus A and P minus A. I'm just rewriting them a little bit simpler, which is the probability that you observe SNP A given that you're a case, and PA given that you're a control. Okay, so that's just, I'm saying that, like, if you think about it, if I take a random control individual, guy that doesn't have the disease, what's the chances of him having that SNP? Well, that's exactly what P minus A is, okay? So, and then this is going to be the frequency in the population, and then this is going to be the frequency of just the individuals that have the disease, okay? So, this is actually why we covered Bayes' rule, okay? So, if I give you these values and the relative risk, I want to figure out what these two values are. Okay, so how do I do that? Well, look, first of all, this guy here, P of having the SNP given the disease is equal to the probability of having the disease given the SNP times the probability of having the SNP divided by the probability of having the disease. What rule is that? That's the Bayes rule, okay? It's exactly the Bayes rule. So we just reverse these two guys, we're interested in this, we know what this is in terms of that, okay? What about the probability of having the disease? So the relative risk is what? It's going to be the probability of having the disease if you have the SNP divided by the probability of having the disease if you don't have the SNP. That's the definition of relative risk. Okay, so if I just multiply that, the probability of having the disease is going to be the relative risk times the probability of having disease given that you don't have the SNP, right? That's just the definition. So then, now the probability of having the disease is equal to the prevalence. That's the definition of the prevalence. And there's essentially two ways that you can have the disease, okay? Either you have the disease and the SNP, or you have the disease and you don't have the SNP. So do you guys know what rule is this? Yeah, the law of total probability, okay? So I'm just partitioning this event into these two cases, right? And then what about this? And so then what do I do here? I just use this relative risk, okay, to change this from a naught to this guy, right? You guys see that? Because this is P plus naught A. P plus naught A is equal to this divided by this gamma. So I just replace it here. Okay, so then what do I do next? I factor out this guy. I mean, look, there's two levels here. One is you can follow what I did, okay? And that's actually not that hard. Figuring out what to do, that's obviously harder, okay? But that's not what I'm asking. All I'm asking you is just to follow the steps, okay, so that you can do it. So then I factor this guy out, okay, here. And then what is this one here? So this is going to be F is equal to this, right? So then what? So P. So how do I do? So basically, if I then take this P plus A and I divide by this term here, right? I'm going to get F. P plus A is going to be gamma F times PA times gamma minus 1 plus 1. Okay? So these guys are all things that I know. I know the frequency of the population, and the prevalence. Okay? I know, and the relative risk. I'm assuming the relative risk. So that's how I get P plus A. Okay? So this is just, at the end of the day, this is just the formula. And you'll have some of these on your homework as well, and some examples. Okay? This is the formula that you use for P plus A as a function of these guys. What is this here? Huh? This is Bayes' rule, right? And what do I do here? What am I doing here? Yeah, just substitutions. Okay. But actually, okay. So what's the? But what about this one here? This is the negative. This is the controls. So the controls is going to be 1 minus probability of. So if I know this guy, right? This is P plus A, right? What is going to be the frequency of the so what is P minus A? It's going to be 1 minus the probability of having, this is the probability of not having the disease if you have A, right? That's going to be 1 minus the probability of having the disease if you have A, right? Which is going to be 1 minus this, because we just figured this thing out, right? So PA minus, right, is what? It's going to be, this is from Bayes' rule, okay? And so if F is small, what happens? Then 1 minus F is going to be approximately 1, okay? And then this is going to be approximately, actually, sorry, this is going to be, yeah, this is going to be approximately 1. And so then this here is going to be what? If this is approximately 1, then if I go back to here, what am I going to get? Actually, there's a typo here, I realized. Okay, there's a typo here. Okay, so basically this value, PA minus, is going to be approximately PA. Okay, so I think this is actually going to be 1 minus F is 1, then P minus given A should be basically P minus, not 1. Sorry, this should be P minus. Yeah.
On the first line of that, P minus A equals 1 minus P plus A.
Yeah.
Why is it 1 and not just A? Because isn't it P plus given A?
It's P plus given A. Yeah.
Why is it 1 minus A minus?
Okay, that's a good question. So think about it this way. You're considering all the individuals that have the SNP, okay? There's some probability that they are, okay, I see you're scaling it. I know what you're intuitively thinking, okay? But let's say I have 200 individuals that have the SNP in this room, okay? Or not in this room, 200 individuals that have the SNP. Let's say 40% of them have the disease. How many of them don't have the disease? 60% of them, right? This P minus A is kind of an of them. Does that make sense? What you're thinking is that what are the what percentage of all the people, okay, have both not the disease and the variant? That would sum up to PA. So PA, okay, you're thinking of something that looks like this law of total probability, okay? And this, okay, but this is like the conditional. Okay, so there's a typo here. I'll fix it next class. But basically, this one is correct. So basically, if the prevalence is small, then this is basically PA. Okay. So then, if this is lambda A, okay, so then this is the formula for lambda A. This will be the statistic. Okay, so here's actually some examples. Okay, so let's say the relative risk effect. You have the minor allele frequency effect, number of individuals. So let's say the relative risk is 1.5. Let's say the disease is rare in the population. Let PA equal 0.2. The frequency is 0.2. So then the case frequency is going to be this, which is 0.273. The control frequency is going to be basically 0.2. So we can use these to estimate the power by plugging them into lambda, etc. Just following what we did previously. Okay. So what if the risk is now 0.2, right? So this is it's gonna be higher, right? So PA plus the case frequency is going to be 0.3, and then the control frequency is going to be 0.2. We're going to use these to estimate the power, okay? So, I mean, that was yeah. That's a great question. You don't. The relative risk, you're assuming the relative risk when you're computing the power. So typically, whenever you report the power, you're going to be like, okay, if the relative risk is 2, then for variance of this, of let's say 20.2, my power is going to be 70%. If the relative risk is 1.5, my power will be 50%. So you actually, every time you assume a relative risk, then that's going to be. The reason why we're talking about in terms of relative risk, instead of assuming the case and control frequencies, is that people intuitively, like if you go into the doctor, okay, the relative risk is what matters. Okay, it's basically if you have this variant, how much more likely you have the disease. So that you can think of that as kind of what people care about. When you're talking about case control frequencies, it's all this like Bayes rule stuff to compute, like if you collect individuals, then it's going to be more common, et cetera. Does that make sense? Okay, so I know this is a little confusing, especially with my typo. This you guys are going to have, on the homework, you're going to have practice problems like this, where you basically do this. What's really important is that you just understand these formulas and have an idea of how to drive them, and then you'll have the slides also that'll help you. Okay. So now let's say it's 2. This is the frequency. What about if the relative risk is 2? Okay, we did that one. What about if the relative risk is 1.5, but the variant is more common? Okay, then you get this is the case, this is the control frequency, etc. Okay, so okay, is that make sense so far? So relative risk is just like how you can estimate how you when you're computing power, how you determine the case and control frequencies. Okay, so okay, last concept here. So we've been dealing with n/2 cases and controls. So now what if you have different numbers of case and controls? Okay, so now let's say that you have n+/2 cases and n-/2 controls. So the statistic, this difference, is going to be what? It's going to be this. Under the null, right, this is still going to be 0, okay? This difference is now going to have a different, instead of, this is going to be an n, this is going to be n plus and n minus. Those are different values. If you use the same concept, okay, so instead of your approximation, instead of assuming that this is going to be 2 pa times 1 minus pa, it's actually going to be this value, which is kind of close to it. Your statistic is going to be, your statistic is going to be the same Nonstrata parameter, be this value here. Okay, so what if n plus and n minus are the same? What do you get here? This is going to be what? N squared divided by 2n, right? And so the 2 cancels. You get square root of n. It's the same. Okay. So you see, it is the same, but it's also, but if it's not the same, you just use this, right? Okay. So, okay. And here's actually an interesting question, and this is actually a grad student question on the homework, which is, what if the size of the control population n- is unlimited? Okay. What is the increase in power? So why is that? So this is a grad student question, so it's not on the homework. But here's the intuitive idea. Let's say I'm interested in a disease that only has 10,000 people in the world that are affected. Okay? So I can't, if I do a balanced study of 10,000 cases, 10,000 controls, 10,000 is the highest number I can ever get. But hypothetically, what if I use all, I don't know how many, 8 billion people on the planet as the controls? Okay, obviously that would increase to some degree my power, right? But how much would the increase be relative to a like if I had more people that have cases. That's what the question is. Okay, so basically if I'm comparing a balanced case control where I have like the same number of cases and controls compared to like how much bigger is the balance, would I need a balanced case control study? So that way it'd be the same as having like, an infinite number of controls. So like what's the, is having an infinite number of controls, is that the same as having an infinite number of cases and controls? Or is there some, what's the trade-off? Okay. That really comes from this equation. Okay. Okay. So yeah, that's the break. Okay.